All right, we are up and running. Homework 11 due tonight. Homework 12 will be posted later today. Studio 8 is due December 9th. And please answer your daily quiz number 24 on Gradescope today. So we are coming to the finite string design, finite state machine design for a finite string recognizer. So what you are doing is a string detector, a bit sequence detector. Our input is X, which is essentially going to change with time. So that's a bit stream coming in. Our 1-bit output is Z, which is supposed to let us know about the string that got recognized or not. And the description for this FSM is that Z, the output, should be 1 if the 3 previous input bits are 0, 1, 0. And that can happen only when 1, 0, 0 has never been seen. So make the output 1 when the last 3 bits are 0, 1, 0. And also you need to check for 1, 0, 0. So make Z1 only when this is recognized, but also when this has never happened before. Now, some of the unstated assumptions that we need to explicitly mention before starting to design this FSM is that there is a reset that starts the FSM, which is essentially your initial state, and Z is asserted when the following bit is seen. So it's going to be a Moore machine because we are waiting for that FSM to go to the next state and then change the output. Okay, so with this, let us go and no, I record my videos using a different software, Zika. Let's see. Let's talk a little bit more about the behavior of this FSM. So X is the input bit stream, and we have some zeros and ones listed over there. And Z is the output that is supposed to give us 0 or 1. It should give us 1 when it recognizes the 0, 1, 0 string, right? So we are essentially interested in two strings here, 0, 1, 0, and we also need to worry about the 1, 0, 0 string, because if you see 1, 0, 0, you can never make Z 1 again. So what is going to happen? You're going to start all the way over here. Let's say this is time 0. That's the initial time. And you're going to see 0. No, it did not recognize the string. Last 2 bits are 0, 0. Did not recognize the string. The last 3 bits are 0, 1, 0, 0, 1. Did not recognize the string. And now you see 0, 1, and 0. Soon after that, your output is going to become 1 because we have recognized that string 0, 1, 0. And then we recognize that string again over here, 0, 1, 0, and then we make the output 1. We recognize the string again over here, 0, 1, 0, and we make the output 1 here. However, once you see the string 1, 0, 0, then even when you see 0, 1, 0, you keep the output 0. Is the bit stream given all at once, or is it given one at a time? It is a one at a time, right? It's coming in one at a time. So you see 0 and then respond. You see 0, 0, you then respond. So it's a continuous bit stream coming in and a continuous bit stream going out for Z. So in all of these finite state machines, it is not static, right? Some things are changing as time progresses. So that's the whole idea about the machine, that it changes from one state to the other. Yes, it is sequentially. All right. So Z is 0 even though the previous 3 bits are 0, 1, 0 because 1, 0, 0 was seen earlier. When did that happen? If you see 1, 0, 0 happened over here. So even if you see 0, 1, 0 here, you did not detect that as a 1. All right, let's move on and take a look at the formal design process. What I'm going to do is, this is sort of my default process whenever I get into like a string recognizer situation. What I like to do is first my reset state, state 0, and from there I draw two paths for the two strings that I need to track, that I need to detect. One path is the things that are being detected 0, 1, 0, and the other path is 1, 0, 0, because I also need to worry about that path because I need to respond to the string 1, 0, 0 in a different way, but I still need to respond to that. So that gives me like a two paths from S0. If I detect a 0 from S0, I go here, then for a 1 I go there, for a 0 I go there. So that's one path. From S0, if I get a 1, 0, 0, I go to S6. Now, the only state in which my output is 1 is S3, only when I see 0, 1, 0. Notice all these guys are inputs, X, and these guys are output, Z. So in this design, I have used 7 states. And if I have used 7 states, that should immediately tell you how many flip-flops and all of that. It should give you all that information. So let's just write it. What is the number of flip-flops that is needed? All right, 3 is absolutely right, because with 3 flip-flops, I can have 8 different states. Right now, I only need 7 of them. Perfect. Now let us start talking about something here. How many arrows do I need to worry about from each state? If you look at each state S0 or S1 or S2 and so on, I need to worry about two arrows coming out of each state, because from each state I could get a 1 or I could get a 0. For S0, I have done that process. If I get a 0, I go to S1. If I get a 1, I go to S4. I have completed that for S0, my starting state. And I've also done that for S6. You see, S6 is the state in which you go, where you go to once you recognize 1, 0, and 0. So after you recognize 1, 0, 0, no matter what happens, you have to continue to stay there. So if you get a 0 or you get a 1, you just stay there while the output remains at 0. Unless the user hits a reset button. So the only way to come out of S6 is for the user to kick things off again, start things off again. Now, what I have missed is S1, S2, S3, S4, and S5. So what I'll do here is, for our same string recognizer problem, I'm going to try to figure out what should I do from S1. So where should I go from S1 if I get a 0? Okay, Ian says S1. Perfect. That I accept that, because if I get a 0 here, I will stay at S1 because I still need to treat that as the first 0 that I got. Right? So I'm going to stay there. You guys agree with that? I'm not going to S0. I'm not going to any other place, but I'm going to S1. All right, from S2, what should I do? So S2, what does the state S2 mean? S2 means I got 0, then I got 1. Now, from S2, if I get another 0, I know I go to S3. But what if from S2 I get a 1? 1 goes back to S0. Okay, so 0, 1, and another 1. You guys are saying that I need to go back to S0? Think about that a little bit more. Yes, because you see, it could be the start of the 1, 0, 0 sequence, right? So from this, if I get a 1, I need to go over there, because that could be the start of the 100 sequence. You guys see that? And if it is not, then you know that it's not going to follow through. It's going to break and come back, and we'll complete that process. All right, so 0, 1, 0. All right, you got that. From S2, you go back to S4. We got that. Now did we complete S2? 0 and 1. Yes. Now let's talk about S3. Where should I go with S3? Well, your computer is a finite state machine. So that's how common it is. All right, let's see. From S3, I don't know where to go from S3 for a 0 or for a 1. 0 goes to S6. Okay, so I 0 means I got a 1, then I got a 0, then I got another 0. That means I got a 1, 0, 0. Right, so I need to go there. Okay, where should I go when I get a 1 there? So from S3, if I get a 1, where should I go? From S3. All right, so you see S3 means your last 2 bits are 1. So you got 0, then you got a 1, then you got a 0, right? So if you get, there are 2 possibilities here. You could get a 0 there, or you get a 1 there. So if you get a 0, we said we go to S6. What if you get a 1? If you get a 1, that means that could be the start of another 0, 1, 0 sequence, right? So we need to go back to S2 for this. You are right. And you see, we did this from for this path, and similarly we could do that for S4 and S5. Let's see, from S4, where should I go if I get a 1 from S4? S4, right? I don't need to do anything. I just treat that as the first one I got. S5, where do I need to go from S5 if I get a 1? S2, right? Because you see, I got a 0, then I got a 1, right? So that could be leading me to the 0, 1, 0 sequence. Yes, so I need to come back over here. And I think we have completed all the zeros and ones here. Every state has 2 arrows coming out of it. So that is essentially like that completes the FSM. So I hope that discussion was helpful. The slides that are just going over the same steps that we have done. Eventually to come up with, we talked about states 2 and 5. We have already done this, by the way. Right. So that's essentially your last state diagram. We have looked at this earlier. We just didn't go through it each and every step. We just did it in a slightly quicker manner. But this state diagram that is shown on the right exactly matches the state diagram that we just drew here. In terms of determining the number of flip-flops needed, are there 2 raised to n states allowed where n is the number of flip-flops? That's absolutely right. A maximum of 2 raised to n states. All right, let's go on. Let me talk about what is the next step. We are not going to do all the steps here because we got the state diagram. But I just want to talk about what would you do to complete the finite state machine. So we are over here, right? So we got the state diagram. After the state diagram, what would you guys do? So this is how many states we have? 7 states. We had 7 states. From the state diagram, create a state transition table. Perfect. So you would write, you would start with writing the symbolic first, right? Write symbolic state transition table. And then using that, you would do state encoding, right? You would do something like S0 is 000, and then S1 is 001, and so on, all the way to S6 is 110. Again, this is an arbitrary choice. I'm just giving you guys the more straightforward state encoding. That's what you would do next. With the symbolic state transition table and the state encoding, you would then write the encoded state transition table. Just as a mental exercise, can you guys tell me how many rows are we going to have in this encoded state transition table? Number of rows. A lot more than 7, I think. Okay. So from each state, you are going to consider the possibility of, yes, absolutely. So from each state, you are going to consider the possibility of the input being 0 or 1, right? So you got 14 rows here. You guys, can you guys picture how many columns are you going to have here? What columns? Instead of numbering them, we'll just name the columns. What are the columns you are going to have in the encoded state transition table? Okay, so Preston says 6. Let us just name them, right? So you're going to start with present state. What is the present state? You're going to have Q, I have 3 of them, right? So I have Q2, Q1, Q0. And then I'm going to have input. So input is X. That's your input. Then you have your next state. Next state is what? Q2 plus and Q1 plus and Q0 plus. And then your output is simply Z. And then if you were implementing this using data flip-flops, then you don't need any more columns. But if you were using a T flip-flop or a JK flip-flop, then you would need more columns. But at a minimum, you would need 8 particular columns and 14 rows. So it's a pretty big encoded state transition table. Let's come back to our problem here. From the encoded state transition table, what would be your next step? The final step is to draw the finite state machine circuit. K-maps, perfect. So we are going to be dealing with K-maps. Can you guys tell me the number of K-maps and the size of K-maps? You are going to have how many K-maps? 4 3-variable K-maps. 4 is fine, 4 K-maps, but how many, what is the size? 4 variable, right? Because you see, you're going to have an expression for Q. So I'm assuming that we are doing this with D flip-flops. If you were using D flip-flops, then you would have D2, D1, D0, right? And then Z. So you'd have 4 K-maps in terms of Q2, Q1, Q0, and X. So size of the K-maps is also going to be 4. And from the K-maps, you should get logic expressions for, if you were using D flip-flops, you would get a logic expression for D2, D1, D0, and Z. Quick question is, what is Z going to depend on? Option 1, Q2, Q1, Q0. Option 2, Q2, Q1, Q0X. All right, think about this. It's a Moore machine. So if it's a Moore machine, then the output will only depend on, right, it depends on what kind of machine. And you can see this. Output is listed inside the state, right? So it is a Moore machine. So if it is a Moore machine, the output can only depend on Q2, Q1, Q0. Maybe not all of them, but they will depend on some combination of Q2, Q1, Q0, the present state. But Z, when you write the equation for Z, it will never depend on X. You guys agree with that? Oh, no, you can't. You still need to include it. But once you do it, you should observe that it is independent of X. All right, after you draw the logic expressions, using the logic expressions, you can draw FSM circuit with 3 flip-flops, and then of course you will have logic gates, many logic gates based on the expressions that you derive for D2, D1, D0, and Z. All right, questions about this process? We are not doing this process because we have done this, and when you do it a couple of times, after that it's just the same steps over and over again. But what becomes crucial in finite state machine design is to take a look at the problem statement, state the assumptions clearly, and then go to the state diagram. So that happens to be the most sort of, that's what tests your creativity, and you need to think about that a little bit more carefully. But after you get to the state diagram, the process is very structured. It's one step after the other. There's not much that can go wrong if you just follow the rules. All right, questions about this example? The finite string recognizer that is able to track 2 sequences, 010 and 100. And it is responding to both those sequences in slightly different manner. Okay, let's move on to this is I'm not gonna do the traffic light controller. It is a little bit too simple. All right, let's do the combinational lock. This is not the final combinational lock design that I want to go for. So it's a little bit more advanced than the previous one, but it's not the most complicated one that we are going to see today. So this combinational lock has a 3-bit serial lock that controls entry to a locked room. So we are talking about inputs that are reset. You have a switch or a button to press enter, and you have a 2-position switch for the bit of key data. So essentially think about it as a 3-bit switch, right? There are 3 switches, and you would have to arrange the switches in the proper combination, and then press the enter key to unlock. So the locks generates an unlock signal when the key matches the internal combination. and the error light is illuminated if the key does not match the combination. So the sequence of steps for a user is press reset to initialize your finite state machine. Then you enter the key bit, right? The first bit. Enter the key bit, then press enter. And then you would repeat that for the second bit position and the third bit position. So after you set each key bit, you would press enter and then go on to the next bit position. In total, you have 3-bit positions, right? So how many possibilities could happen for the internal combination? Like how many possibilities can you have for the internal combination? Eight. Yeah, absolutely. So eight particular combinations, right? You can have 000 any to 111. Any one of those 8 as the internal combination. There's a question online saying, shouldn't there be a 3-position switch if there are 3 bits? No. So the switches itself are 01 and 01 and 01, right? So there are 3 switches that you could have them as on or off. And there is a enter key over here. So you would set this, hit enter. Then you would set this, hit enter. And then you would set this and then hit enter. Each bit being entered at a time. You got it? Yes. So hardware wise, there is one switch. Well, you could have 3 switches or you could have 1 switch. That really doesn't matter to the problem. What matters is the signal is coming one after the other. The signal is being monitored one after the other. Let's see what happens if we don't set any bit and press enter. The unlock, the error light will be illuminated, right? So there is a default position for the switch. It might be a 0 or it might be a 1. So if the user just presses enter, it will take whatever the switch position is. They might be correct or they might be wrong. But if they are wrong, the error light will be illuminated. And I hope you guys see that there are already some characteristics about this combination lock that are kind of bothering. The first one that jumps out at me is that if I'm doing this one position at a time, the moment I know first bit is wrong, I will switch it. And the moment I know the second bit wrong, I will switch it. And the third bit is wrong, I will switch it. So once I figure out the wrong sequence, I can obviously put in the right sequence and keep pressing enter. So it's not like what would have been better is if there were 3 different switches and the user was supposed to enter the 3-digit code and then press enter, right? It would have been a little bit better. But even then, out of 8 tries, they could get lucky and get in. All right. So it's not a very advanced combination lock, but what we are trying to convey with this problem is how would you design an FSM in this particular situation? Safest bet is to okay. Yeah, hit enter to see if you're right. Yes, that's a problem here. Yeah. All right, so let's try to look at some specifications of this problem that we have not explicitly mentioned, which is when should the error light be asserted? Should it be asserted after every enter key, or should it be asserted after all the 3 are checked? And I hope you guys will agree that it should be checked to get a little bit more security, not that it is great, but to get a little bit more security, you would want the error to be asserted after everything gets entered, because it would be obviously a bad idea to indicate an error has occurred immediately after you see the first bad bit. So in our design, we will illuminate the error after the full combination has been entered. So the error thing gets illuminated, the error LED gets illuminated only after we track the full combination. There's another question on the chat box. I'm assuming we can easily make these FSMs on our basis 3. You're absolutely right. You can make them very easily on your basis 3. Let's take a look at the block diagram for this combination lock. You have this reset button to start things off. You have this enter button to essentially say, go ahead and check my bit. And there is a key in. So that's the key you are pressing, right? For the 3 locations, L0, L1, L2. So L0, L1, L2 are the internal combination. The output of the combination lock is unlock or error. So if we look at all the inputs and outputs for this FSM, your reset, enter, and the bit that you are keying in every time, right? This is the key in is being compared with L0 the first time, then L1 for the second time, then L2 for the third time. L1, L2, L3 are the user set lock code. That's the internal combination. The outputs are unlock and error. That's the idea here. So now the way the diagram is shown, key in is just one line, right? So it's just one switch essentially, but you could have it as 3 switches and the signal coming in at 3 different times. Our goal will be to draw the state diagram, because we know what to do after the state diagram. The same old process we just completely described. So we'll get to the state diagram, and then the steps will be after that. The steps will be the same. So what sequences lead to opening the door? That's what you would start thinking of first. And then we would do the error conditions on the second pass or the second path that we looked at in the string recognizer. Remember, we had 2 paths. One was for 010 and the other one was for 100. Now we are going to have 2 paths. One is for the good user and the other is for the wrong user. And we still need to have the bad path, because we need to wait until the user enters all the bits, all the 3 bits, and then we can say error or not, right? We don't want to respond to it immediately. So that's why we need to keep track of the second path as well. So this is your final state diagram that is shown over here. I'll walk you guys through the steps. It might look a little bit intimidating, but it's really not that hard to follow through. So here is your starting state. When you are in your starting state, the way you get to this is by pressing the reset button, right? So your user presses the reset button, you go to the start state. And from the start state, if the user presses reset, they continue to be over here. Or the user does not press enter, you continue to be in that start state. Now, the moment the user enters the enter key, like presses the enter key, while the reset input is inactive, then you go to a comparator. And the comparator is for the bit 0, the least significant bit, or you're essentially comparing key in with L0 first. So when you compare that key in with L0, L0 is your internally set combination and key in is the user input. When you compare that, two things can happen, of course. It can be equal or it is not equal. When it is equal, you go to an idle state in which you stay there until the next enter key is pressed. So until the next enter key is pressed, you stay in the idle state. But from here, you go to, when the user presses the enter key the second time, you go to the next comparator, comparator 1. Over here, you compare key in with L1. Again, you might get it to be equal or you might not get it to be equal. If you get it to equal, you do the same thing. You go to an idle state 1 in which you stay until the user enters, presses the enter key. When they do, you go to the next level comparator. Comparator 2. Compare key in with L2. If they're equal the third time, then you go to the done state in which you activate the unlock signal, and only when the user presses reset again, you come back to the start state. So that is essentially your good path, right? So this is the good path. The good user would follow that path. Now let's take a look at, what would happen if, so what happens if a switch is changed in the idle state? Nothing would happen. To get out of the idle state, the user has to press the enter key. Only then the next level comparator will be operational. So the switch, once you go to this, you cannot go back, right? I think you're talking about going back to this. So if you're using one switch to do this, of course you're going to have to use the same switch for all the 3 positions. But if you change the switch, wouldn't it change to the opposite idle? Huh? If you change the switch, wouldn't it change to the opposite idle? No, so the way you come out of any state is by the input that causes the transition, right? So if I'm in idle 0, no matter what I do to the switch, I'm going to stay in idle 0 until I enter, until I hit the enter key. Which, in other words, if I get it right the first time, that's it. I don't need to care about that anymore. The finite state machine can only go from up to down. It cannot go the other way. All right, let's take a look at comparator 0, and let's take a look at what would happen if the bit key in is not equal to L0. If the first key is wrong, we go to an idle 0 complement state, which is like a different state. We stay there. This is kind of like a fake idle state for the bad user, right? So you're staying there. So essentially you're responding to the good user and the bad user in the exact same manner. However, the only difference is if they get it wrong over here the first time or the second time or the third time, you go to the bad path in which the eventual signal that gets activated is error. And there are 3 ways of going to that bad path. The first bit wrong, the second bit wrong, or the third bit wrong. Any one of those 3 bits wrong, you go into that bad path. But you still wait for the enter keys to come in. So you're still responding to that bad input sequence the same way as you would to the good input sequence, to indicate to the user that everything may be going okay, until you go to the last stage. From the error, again the user has to enter, hit the reset key to come back. All right. What kind of finite state machine is this? Mealy or Moore? More is absolutely correct. More is right. So Preston says, I'm a bit confused on how we get from comparator states to idle states. Since the switch is always 1 or 0, wouldn't there not be any time for the user to change the switch? So here, look at this. You are in the reset start state. Then you press enter. The moment you press enter, the user presses enter, the comparator becomes active, operational, and the comparator compares the key in ki. Ki is the user input from the switch with the internal combination L0. They might get it right or they might get it wrong. No matter what happens, they end up in a idle state, which is essentially, think of it, idle state as a state in which you do nothing, you just stay there until somebody hits enter again. So until the next enter key gets pressed, you will stay in that idle state. So we change states in the idle states and we change the switches in the idle state and the start state. Absolutely right. Yes. The comparator is combinational, right? So that would give you the results automatically. There's nothing stopping it from getting compared. All right. So we talked about the fact that this is going to be a Moore machine. You are going to have a lot of states over here, as you can imagine, and that would simply increase the size of your FSM. You know, it's a good combination lock, but still, you try it 8 times. You don't even need to try it 8 times. The worst case scenario, you try it 7 times and you will get it right. That's the worst case scenario. So we could do better than this. So we'll take a look at another. We need more bits. We need more bits. That's one. Or we could have an alarm, right? So if the wrong sequence of bits get entered, we could create an alarm situation to kind of find out that it's a wrong user, right? So that's what we have in our next combination lock. This is kind of the most advanced finite state machine combination lock we'll be looking at over here. So if you guys were not paying attention until now, this is kind of like the big combination lock finite state machine that we are going to look at. So I would encourage you guys to zone in now. We have two debounced push buttons, X and Y. They are being both used to enter the combination. And the sequence that opens the lock is XXYXX. So only if the user enters, or I should say pushes the buttons in that sequence, push the button XXYXX, only then the lock opens. These are push buttons, these are not switches. The second feature is, if you press Y 3 times in a row, we can reset the lock. So you can go back to that initial state if the user presses Y 3 times in a row. This is something that the good user understands, and maybe not a bad player, right? So somebody who is trying to break in, that they don't know this. But the user understands that, okay, if I happen to maybe push the wrong push button, there is a way for me to get out of it by pressing Y 3 times. The third feature is, at any time X is pressed out of sequence, an output signal sets off an alarm to indicate the lock is being tampered with. So for example, if you press X, X, and the third X, that is indicative of X being pressed out of sequence, and that would trigger an alarm. And there is a way to get out of that alarm situation by pressing Y 3 times. When the lock is open, pressing either X or Y will cause the lock to close without signaling an error. The assumptions, you need to state any assumption that you make, what does the each state represent, and what input conditions cause the state and output to change. We need to state all of these things moving forward. But I hope from this you understand the features of the lock, about reset, about the alarm, and the sequence that opens the lock. This is essentially the answer. Again, lot of states over here. This guy has 11 states. So you might be going, whoa, what is this? Let me walk you guys through the good paths first, and then we'll talk about the bad entries. So we'll start with S0 right here. You come to S0 with the reset button, right here. When the user enters the reset button, you come to S0. Then this is a mealy machine, by the way, because you see the input is X, the output is 0, 0. The outputs that are being used are A for alarm and U for unlocked, and they are occurring in that same sequence, A followed by U. So let me just point it over here. This is A for alarm and this is U for unlock. So when the user is in state 0, the initial state, and they press X, the push button X, they go to state 1. But while they are going to state 1, the alarm is not triggered and it is not unlocked. The combination lock is not unlocked. Right? So S0 to S1. Then you see, let's go back here, zoom out. S0, you go to S1. That's the good. Maybe I use a different color for good. So green. So that's good path. From S1, you press X again, you go to S2. From S2, you press Y, go to S3. From S3, you press X, you go to S4. From S4, you press X, you go to S5, where you unlock. So you see, when you are going from S4 to S5, that happens when the user presses the last X. And when they do, no alarm, but unlock is 1, meaning this is my unlocked state. From the unlocked state, no matter what I press, X or Y, I go back to the reset, the initial state. So I lock, no alarm, and then I go back. So that is, if you guys see this, this is the good path, right? X, X, Y, X, X. Now, let's talk about this path right here. This is the reset block. From S0, in fact, from any state, if you press Y 3 times, you go back to the initial state, right? So from S0, if you, so let us highlight this in blue. From S0, if you press Y for the first time, you go to S6. Press Y for the second time, you go to S7. And you press Y for the third time, you go back to S0. So press Y 3 times and you go back to reset. And that should happen from every state. And we'll take care of that. But that's our reset cycle, reset loop. That's our reset loop. Everywhere over here, no alarm, no unlock. All right. We have talked about the reset block. We have talked about the unlock block. Now let us look at the alarm loop. So when do we go into the alarm situation? The only time we should go there is if the user presses X out of sequence, right? So what would be the first time they would do that? Well, X, X, then instead of Y, if they press X, they should go to S8. You see that? X, X, and X. So the moment they press the third X, alarm goes off, it does not unlock, and you end up in S8, where that is the alarm loop. It's not a requirement. We chose melee because we wanted to respond to the wrong push buttons immediately. It's not a requirement. All right, next, from S8, once the alarm goes off, what would happen? Well, if somebody is trying to steal something, then they might panic and they might hit enter, they might hit X many times in a panic mode. And if they do, they continue to stay at S8, where alarm is keep going off, but it doesn't unlock. But from S8, they should still be able to press Y 3 times and get out of it, right? So from S8, if they press Y, you see this, they go to S9. Second Y, they go to S10. Third Y, they go to S0. So you see that is a way to get out of it. But while they are in S9 or they are in S10, the alarm still keeps going off. All right, that's so those are those things, right? But you see, if you are in S8, that means you have pressed X out of sequence. You press 1Y and 2Y, and then if you don't press the third Y, you go back to S8. You still are in that alarm state. There are other ways to go to S8 as well, right? So from S0, if you hit Y to begin with, you go to S6. But if you hit X here, you go to that alarm state because that is an X that is out of sequence. The only sequences that you should see from a good user from the starting state are XXYXX or YYY. If you get something like YX, you should indicate that the alarm should sound. That should also happen from S7. Y, and then X, you go to S8. If you go to S8, which is the first state in which alarm is going off, you press Y, you go to S9, hoping that you can reset it. But if from S9 you press X again, you go back to S8. So I hope you guys now see the three sort of paths here. One is good path leading to unlock, the reset loop over here, and the alarm block over here. I think I left off one more item here, which is the ability to reset from any state, right? So how would you reset from any state? So for example, if you go to S1 and after you go to S1, you want to reset, where should you go? You press Y, 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 right? So from S1, S6, S7, back to S0. And suppose you wanted to do this from S3. You press Y, you go to S7. Then the second Y, oh, hold up. From S3, oh yeah, there is already a Y, right? So Y, Y, and then the third Y comes over here. And if you go through this from every state, when you press Y 3 times, you will go back to state 0. All right, questions about the finite state machine design for a little bit more realistic and a little bit more advanced combinational lock, which operates on 2 push buttons. Questions, you guys? All right, so looks like we are good. I'm going to stop recording here.